a qubit is basically a single unit of information in a quantum computer. It's maybe not the most whimsical of names, but it's literally, if you take the Q from quantum and add it to bit, or I guess the QU from quantum and add it to bit, you get qubit, right? We can predict what a single qubit will do by keeping, so like if we want to actually simulate a quantum computer, if you've taken a quantum mechanics class or something like that, you'll know that we can simulate all of that with basically linear algebra. So, and that's, if you're not super familiar with linear algebra, or it's been a while, it's been a hot minute, we do have a pretty good appendix covering what you need to know in the book, if you need it. But basically, a qubit can be represented as a column vector of two complex numbers. So like a regular bit in a classical computer is just a 1 or a 0. A qubit, or a singular unit of quantum information, can be represented by this vector of two complex numbers. So here I'm actually importing qtip and using qtip to actually kind of represent a quantum, in this case, their quantum object class, but it represents a single qubit. We say that our qubit has this state. Basically, by manipulating these vectors that represent the state, and matrices, which represent the operations that you're going to do on them, whether it's like the H operation that we saw before, or ones that operate on multiple qubits at once. You basically just multiply them all together, and then you get a vector at the end, and then that basically represents, you can use like Born's rule, or you can use your software tools to figure out what you would measure with what probability at the end. We've got a qubit. What can we actually do with a qubit? The sample we've looked at so far kind of gives us a pretty good outline of that, right? Basically, we can prepare a qubit, so that's kind of like the using statement. We can do things with the qubit. We can do operations. So that's like applying the H operation. We'll see a few more examples of different types of operations we can do. And then you can measure a qubit. So what's interesting, though, is when you measure a qubit, you don't get that full vector of two complex numbers back out. That's a way to represent the information it has, but that is not accessible to us. What we get out if we measure a qubit is a classical 1 or a 0. So it's kind of interesting. If I measure a quantum register, it gives me the same type of information as if I measure a classical register. And so a lot of the trick and art and nuance of designing quantum programs and quantum algorithms is trying to figure out how to get the states that represent your qubits kind of arranged in such a way that when you measure it and kind of collapse it into this classical information, that you either have a high probability of measuring what you want, or quantum algorithms can actually be deterministic. And we'll see an example of one here in a minute. But so it's not strictly speaking a probabilistic sort of device. Now that we've kind of seen, this is our sample, we have each of those three kind of covered there: preparation, operation, and measurement. We've seen one way that we can kind of interact with Python and Q#, which was, again, Python saw, we used the Q# Python package. It managed to kind of get and compile Q# code in the same directory and add it to kind of our Python instance, I guess. So another way we can do this is we can actually directly provide text or strings for the Q# package for Python to compile directly in our Python code. So here you can see I'm using this Python function called compile, and basically providing this big block quote of what is valid Q# code. And so I'm actually just going to ask it to kind of compile that for me. And now, just like as if it had kind of uploaded this from a local file, I can run it, and I can actually, it's exactly the same. So it kind of depends on which way you like doing things. I kind of like writing the Q# code in my editor where I have IntelliSense and syntax highlighting and stuff like that, and then can importing it into the Python. What we actually defined in this code snippet, we opened one of the library namespaces actually, so called diagnostics, and we defined an operation called prepare qubit. And what's happened is basically we've asked for a qubit from the runtime, and we're going to use a function from the diagnostics package called dump machine, which basically says, okay, this quantum program is going to run on a specific target machine. Wherever, like, when we get to this point in the program, I'm going to ask the target machine, please, can we print out everything you know about yourself? So if this is a simulator, the simulator is keeping track of those vectors and matrices and stuff like that, all the linear algebra stuff. And so it's going to print out all the linear algebra stuff. And so what you can see here is basically a nice kind of formatted version of the values in that vector. So basically the vector would be 1, 0. So there's no imaginary component here. And the bars, so this stands for measurement probability. So if you were to measure this qubit, we would 100% of the time measure a 0. And that makes sense. This is a good sanity check because anytime we ask for a qubit from the runtime, it should be provided to us in this state. So it should be provided in the 0 state. It's kind of kind of a built-in promise and or assumption that we have with the compiler and runtime that when we ask for a qubit, it'll be in the 0 state. That's the same state we saw earlier that we actually had written in QTIP. This dump machine, it kind of feels a lot like printf debugging, which is, I mean, we've all done it. It's a very helpful technique. So dump machine kind of really can help us inspect and see what's going on with the different operations and things in our program. So again, I'm going to import from our namespace in the separate file in our directory. I'm going to import qrng with diagnostics. So basically what I've done now is I've thrown in a couple different of these dump machines throughout the program. So when we first ask for a qubit, great, it's in the 0 state. It's exactly what we wanted. After we apply this H operation though, so the Hadamard operation, what you can see is it basically shifts so that both the 0 and 1 kind of state or measured state vectors here have the same amplitude. So what that means is our column vector is now basically, technically it's 1 over square root of 2, 1 over square root of 2. Because you have to square these amplitudes to get to a measurement probability. But you can also see that those are equal. Basically, you can think of a Hadamard operation as something that can put a qubit in superposition. Like I noted before, dump machine only can show you the information that the target machine has about itself. If we were able to run this on hardware, which actually technically I could right now, but everything is in preview and I'm not sure the NDA allows for that. Dump machine can only show you what the actual target machine knows about your system. If it's hardware, it might report things like temperatures or other sorts of like hardware parameters, but can't actually tell you what the vector that represents your state is because it doesn't know that. So this is all good, but we've mostly been working with a single qubit so far, right? That may not be the most interesting. So what if we want more qubits? What do we do then? When you do operations with multiple qubits, that's basically when you have the possibility for entanglement. So kind of the two core features or phenomena that we can leverage on our quantum devices that are uniquely quantum are superposition and entanglement. So using Q# with Python, we can also explore what entanglement looks like. So again, I'm going to import an operation here called entangled qubits. And I'm going to so this is again code that's defined in that separate file. Now, if we're allocating 2 qubits, there's basically, if we were to measure both qubits, there's 4 possible outcomes, right? So each qubit can be a 1 or a 0. That's 2 to the 2, so that's 4. And how you can read this is basically each of these lines is one possible measurement outcome. So this would be both of them measuring to 0. This would be the first one measuring to 1, or 0. First one measuring to 0, second one measuring to 1. And so we see when we first ask for the qubits from the runtime, they both show up in the 0 state. And that's why this is 100%. We know we are in the 0, 0 state. After we do entanglement, though, what you can see is now our amplitude, or our measurement probability is split between both 0, 0 and 1, 1. And again, it's kind of this even, kind of like we saw with the H operation, it's a superposition, but what's interesting is there's no chance we measure a 0, 1 or a 1, 0. What that tells us, though, is there is never a way that we will measure a 0 on one qubit and a 1 on the other. So we can measure one of our qubits and know for sure what the other qubit actually is, because there is no probability that it could be the opposite of what we just measured, if that makes sense. We've excluded the middle. And you can do this with like 1001, like this is a particular, just one particular instance of entanglement. It doesn't always have to be exactly 0011 or, however many qubits you have. No matter how many times we kind of run this entanglement generation protocol, when we go to measure our qubits, we're only, like I said, only going to measure, in this case, both 1s or both 0s. Now, this is a really unique resource that we can leverage to actually work with our QRNG that we had from the beginning and actually use it to share this randomness from between two people. And that actually that protocol or kind of area is called quantum key distribution, and is an interesting way we can take existing quantum technology and actually upgrade our cryptography kind of landscape, so that it's not quantum being the bad guy, quantum is helping to build better solutions. I want to very quickly kind of show you one more quantum algorithm to kind of show you, we looked at some very basic, hello world sorts of things. We looked at how we can make superposition and entanglement. And now I kind of want to show you an example where we put all that together and actually write an algorithm that allows us to solve a problem. The problem here is still kind of constructed. We call it like a toy problem or something like that. But it actually represents a very useful subroutine that you can use in larger algorithms, which are quite frequently the most useful quantum algorithms that we know of right now are usually what we call hybrid algorithms. So they have a bunch of classical steps and processing, and then there's some subroutine, some quantum subroutine that kind of iterates with the classical algorithm, and that's how you get your answer. I'm going to set up the toy problem for you. This is going to take some story time. And just so you know, these characters, Merlin, Nemune, Arthur, all make a lot of appearances in the book as well, because we have to come up with some kind of toy problems. We might as well have some fun characters. So we have a very Camelot theme, which actually comes from, there are a lot of quantum theory papers that kind of involve Merlin and King Arthur and stuff like that. Imagine Camelot. And we have the Great Wizard Merlin and the Lady of the Lake Nemune. So both of these are, very, very smart, lived for a long time sorts of folks. And they're kind of trying to decide what to do about the Kingdom of Camelot. And Arthur and Mordred, spoiler alert, King Arthur, and Mordred are currently fighting for the throne. So Mordred, I think, is Arthur's half-brother. Doesn't matter. They both want to be king. So Nemune, being the Lady of the Lake and being as, elegant and aloof as she is, wants to make sure that Merlin is going to be a good counsel for the king. So Merlin signed up to basically mentor whoever the new king is, and is actually going to pick who he wants to be the next king. Nemune doesn't really care who he picks, though. She just wants to make sure he's going to do his job, basically. So the kind of question or problem here is there a way for Nemune to make sure that Merlin is going to do his job, but without having to kind of learn the details about what Merlin's going to choose in terms of who he's going to make king and stuff like that. And turns out we can kind of turn this into a game. Games are a great way to kind of set up a problem that it's easy to solve, or to make it easier to see how you might solve it. So we call this game Kingmaker. Nemune wants to ask Merlin a single question of the form, basically, should a particular heir be the king? So she could ask, should Arthur be king? Or should Mordred be king? And Merlin has to respond with either a yes or no, revealing absolutely nothing else. So basically, given that there are 2 possible questions and 2 possible answers that Merlin can give to each question, we have kind of this table here. So Merlin can have basically 4 strategies. If Nemune asks, hey, is Arthur going to be king? If Merlin actually picked Arthur, he'll say yes. If he picked Mordred, he'll say no. He could actually also be lazy or be trying to just get Nemune to go away, and he could say yes to both questions or no to both questions. So basically, Nemune wants to make sure that one of these first 2 cases is true, and that Merlin's going to actually pick somebody and not just go hang out, smoking his pipe with Gandalf or something like that. So yeah, and that's basically, so what we want to know is Merlin using one of the first 2 strategies or one of the second 2 strategies there. And we can kind of model this as a 1-bit to 1-bit function. So basically, of the inputs are Nemune's questions, the outputs are Merlin's responses, and we can basically diagram each of those strategies as one of these 1-bit to 1-bit functions. You can see we're getting closer and closer to a mathematical thing. Now we can actually kind of arrive at what is the DeutschJose algorithm. So this is a quantum algorithm that if we are given a black box quantum operation called an oracle, which takes 1 qubit in, and acts on 1 target qubit that you get out, we're promised that the oracle is either constant or balanced. So this oracle represents basically Merlin's strategy. And we want to figure out whether the oracle is constant or balanced. So the constant or balanced thing basically refers to, are we in the Merlin's going to do his job case, or are we in the Merlin is going to slack off case? And you can see that here, basically a balanced function is going to be one of these first 2, because basically all the inputs go to all the outputs, and then the constants are basically all the inputs mapped to a single output. That's basically what that means. The balanced ones here represent Merlin doing his job. So ideally, when we try to figure out what type of oracle this is, we want it to be balanced, not constant. We're actually going to be able to solve this in just 1 query to the black box, or 1 query to this oracle. Now, given our formulation, that might not seem like a lot of savings, because if we were to do this classically, we would just, if you were Nemune, I guess you could probably ask Arthur both questions, right? And you would then know for sure which of these 4 cases, or which of the 4 strategies Merlin's using. But we don't actually care about knowing what his specific strategy is, right? So right now, I can, the quantum algorithm we can use allows us to go from 2 queries to 1 query, which doesn't sound like super great. However, this generalizes to n-bit by n-bit functions. So if we had n different questions and n different responses that Merlin could give for each question, it would still only take us 1 query to find this out. Basically, we go from an order n scaling to 1, so that's like the quantum speed up that we see for this problem. If we want to look at, trying to make it show me more code at once. If we want to look at the kind of the key operation here that checks if an oracle is balanced, it takes an oracle as input. We basically use 2 qubits. So we call them control and target. We prepare one of them in superposition, and then use some other sorts of specialized quantum structures in Q#. One example of this is within apply. So it's a common pattern in quantum algorithms to basically do some preparation, do something, in the middle, and then undo your preparation. And so the within apply block structure makes that really easy to do because I don't have to remember to undo everything at the end. It's kind of like having automated memory management, or at least that's kind of what it feels like to me. I don't have to manually manage this. Q# takes care of it for me. That's kind of the basic gist. All of this is in actually chapters 6, 7, and 8 of the book, basically part 2 of the book. you kind of really get into writing some quantum algorithms and stuff like that. I can real quick compile some of this stuff in line. And if I want to run, so I have basically stored here using the zero oracle. So the zero oracle meaning that's where Merlin just says no to all of Nemune's questions, which means he's not going to do his job. And we want to check to see if that's balanced. So balanced here meaning that's the good case. So is the zero oracle balanced? Is false because it doesn't actually match. So I guess long and short of it is, yay, the algorithm does what we expect. And if we do this for the one oracle, that should basically do the same thing. They both will say false because they are both not balanced oracles. Now, if we run one, is the not oracle balanced? Then, surprise, surprise, it is. And that's basically, our one query to actually find that out. There's a lot more details to this. We have an entire chapter dedicated to this. I would strongly encourage you check out a lot more of the details. There's more than I can talk about here. But basically, the long and short of it is we took a problem that would normally take n queries to solve and did it in one. Yeah, we can basically use some of the testing stuff in Q# to basically write tests to make sure that, each of those oracles acts as we think they should. So we have verified that Camelot's future is safe, and Nemune wrote a quantum algorithm to make sure of it. So and also Nemune is the Lady of the Lake. She basically was the person guarding Excalibur in the lake, prior to King Arthur getting it, assuming that Merlin is still willing to do his job.